if n is a certain power of p, say p raised to be greater than or equal to 1. Then we say here we have a capital D. This corresponds to the square of capital D in our situation. But I'm not going to say something more about this. So if D x is equal to the power of c still, c is less than 1/2. Maybe c is just equal to 1/2 or very close to 1/2. This has been done by the Van-Beer-Rabinic Deradoff theorem. It's solved. But if C is even it is very slightly greater than 1/2, that they call it the sort of stronger version of Van-Beer-Rabinic Deradoff theorem. But it is very in general. Still now it is unsolved. We know no one can solve it. Although there are very strong conjecture like the C equal to 1 minus epsilon. That helps them. I can't pronounce the name very precisely. Other conjecture. In this case, they got a certain very significant results, but in general, they couldn't put the absolute value in the sum. So still it may not apply to our problem directly. But here we say we impose the condition D dividing here, although this D is slightly different than D. But if the C in my way is like this. If C is greater than 1/2, that is a double of this number. And if we make a constraint, which is the D dividing the smaller p like this p is the same as that, then we can bound it with some. We only need this constraint, but in our question, this is no problem. That never change. Essentially, that never change the main terms. The main terms is still the S2 is greater than S3. But this implies, we may try say if D approximately has the order like the square root of x, but every prime factor of D is less than a very small power of x, then D could be written as the factorization in my mind. Then for the RU, we can arbitrarily, we have a very flexible choices for the range of R. Then in our estimation, that make more and more variables. The maximum number of the variables, we have the summation over 10 variables or something like this. But they give us more space, more room to make safe. Eventually, we achieve the estimation and the proof this way. So this is mainly what I can say. It's like here. Any question? Any question? What's the bounds? Actually, let me say, first I I say we can bound this. I say this is just then first I mention this, then I will say something about the exponential bounds. If we use the Binnet-Dragov notation, maybe it's different. Maybe at most we have the power of this one, right? But we can prove sigma is equal to O. We just say a power of the natural log, which is K is a large constant. Actually, it could be arbitrarily large. We need to prove this. Then the process of reducing the sums to estimate a certain, that should be a long process. But what I can say is, reduced to one thing is the so-called Grossman sum. That is the sum. We just use the algebraic notation. It is, we say it is C mod D, but it's a reduced summation. E this is the code here, let me say something. Let me say something. We say whenever C is co-prime to D, then we say the C bar is the solution such that C is just a multiplicative inverse. C bar multiplied by C. Then here, for this one, we use a weight bar. Still now, I mean, yeah. It helps us to save a square root of essential from the trivial estimate. And the last, sorry. The last one I just mentioned, the deepest result used in the proof. It could be, say, a multiple Grossman sum. That's a so-called Birch-Barbieri result. It is a consequence of the Weiss conjecture proved by Deligne. That should be in the surface case. Yeah, also it is a multiple similar to that, but there are more variables, something like still it saves the square root from the trivial estimate, like this. Anything else?
Other question?
So usually the integrated class of prime to the boundary less than 7. How often do you pair it?
We actually, our method contains a lower bound of about how many pairs less than x. But this comes from, if we use a Cauchy-Schwarz inequality, it's easy to get it. But it may not be very good.
What's the order for?
It should be using Cauchy-Schwarz. We say the number of the pairs of with edge P1, P2, they are Pi less than X and P1 minus P2. Of course, it should be greater than 0. We say less than. It is greater than or equal to a constant C times X times a negative power of the logarithm. We say it is B. Using Cauchy-Schwarz, but this B could be very large. But Cauchy-Schwarz is not difficult to get.